All right, guys, so we're going to try to do this digital lecturing just to deal with my little bit of travel schedule we have. I'm going to be doing things out on this board in my office. I'm going to be using my notes. I suggest I have a posted version of these, so probably is helpful to be looking through these as you're watching me do this, okay? So we're going to have two videos today, and first we're going to talk about one of the other main crystal structures that we care about in this class. So we're going to talk about the hexagonal closed packed crystal structure. So the closed packed in here means that we're also packing atoms into our microstructure as well as possible. So that also means we're filling 74% of the space. Okay? And the term you're going to see for this, and I apologize if there's a bit of a glare, so again, please check your notes. This would be HCP materials. Okay? And there's lots of things that we care about as engineers where we're going to use these type of materials. So things like titanium, zirconium, magnesium, cobalt, zinc, beryllium, and hafnium. So there's a little bit of variety there, but if you look at these, a lot of the materials or the metals that are really, really light are in here. So magnesium and beryllium are the lightest metals that we can use to design with, and titanium is a good example of something that's has a relatively high strength for its given density. Okay. So you notice we called it hexagonal closed packed, which means it's not cubic. So we're not going to start by drawing a cube. Instead, we're going to start by drawing those closed packed planes. All right. And I'm going to draw that same one I did the other day when we talked about FCC. So I'm going to draw 6 atoms packed together in that closed packed plane. We're going to call that row of atoms site A. And we can sort of drop in other possible sites. And again, this should be sort of on your mind from last time. If we wanted to put a row of atoms on top of this, we could put it at site B here. Or we could put it at site C here. We have sort of two options. We need to pick one. So what we're going to do is we're going to take it. Our first row is at site A. Our second row, we'll say we'll put it at B. And the difference with hexagonal closed packed is for our third row, we're going to go back to A. Okay? So our stacking sequence is going to be A, B, A, B, A, B on forever. Okay? So that's really the only difference. That we repeat and we have this little repeating unit of 2 stacking sequences rather than ABC, ABC that we saw for FCC. Okay? Now because it's a hexagonal lattice, we're also going to have to draw it a little bit differently, and I'm going to draw this in 3D. So the way I'll do this is I'm going to draw one of those top planes. So it would really be this second A plane, and then I'm going to draw the B and the A plane below it. Okay? So I'll make a hexagonal shape, and then I'll have an atom in the center. And if I want to, I'll often see these things connected like this. All right, so that's this A plane right here. I'm going to draw B plane below it, and then the other A plane below it. It actually turns out it's a little bit easier to draw that first A plane when I do this. So I'm going to sort of trace down those 2 atoms in that back row, and I'm going to draw where the guys are that are going to be underneath it. Connect them. And then I can do the same thing for the atoms on the side. And then the same thing for the atoms on the front. I have to put my atom in the middle and connect everything. Okay? But I also want to draw this B that's in the middle. So what I'll do is I'll have one atom that's above this point, halfway up. Another atom that's above this point, halfway up. And then a third that's above this point, halfway up. And I'm going to connect those just so we remember that they're all in the same plane. All right? So we need to define axes of interest for this crystal structure as well. We're going to define 3 using the letter A, so A1, A2, and A3. And all of these are going to be in the close packed plane. All right. So I'm going to draw A1 coming out right here. A2 is going off to the right. And A3 is coming out the back here. All right? That defines everything in this close packed plane. We also need to describe how we're building up. And we're going to call that axis C. Okay? So coming straight out of the board, straight up on this board is C. So C is perpendicular to the close packed plane. All right? So in many ways, this is still very similar to what we saw with FCC. If we pick a given atom, we still have 12 nearest neighbors, okay? So I'm going to pick this guy in the center. I have 6 atoms around it, another 3 right below it, and then there would be another 3 right up here on top, okay? So we have 12 nearest neighbors, just like FCC. And we're going to use these axes to define directions inside of this crystal structure, all right? And I'll try as best I can to sort of use half the board, leave the half I just worked on, and come back and forth, okay? So we're going to describe directions and planes using the similar type of notation, but now we have 4 different axes we're using. We have A1, A2, A3, and C. And we're going to define specific directions with these square brackets. And we'll say, what's the H, what's the K, what's the I, and what's the L that describes that. And in the same sense that we used before, we use the triangular ones for a type of direction that's crystallographically equivalent. And we'll use parentheses for a specific plane. And then we'll use squiggly lines. And again, if you can't quite see this very well, please check your notes. We use those for a family of planes, okay? There's one added complication here. So before, when we had all of our axes being orthogonal, we didn't have to worry about which things we choose here. But now we have a situation. So A1, A2, and A3 are not independent of each other. They're all related in some way. So I can't just pick any number I want for them. So I actually have to set a rule, and I have to use what are called Miller-Bravais indices. And this gives us the rule that I has to be equal to negative the summation of H plus K. Okay? So we can, this is a little bit more complicated, but the reason we do this is it lets us sort of describe crystallographically equivalent sets of indices in a way that looks the same. So it gives us some sort of intuitive feel for it. And to see that, let's sort of pick a few of the important planes and describe them, okay? So this top plane, so that closed packed plane, is something that we're going to call the basal plane. All right? And that would be the planes of type 0, 0, 0, 1. Okay? So that would be, if I want to draw it on here, that would be this top guy right there. All right? I can also describe a few other things that are important. So the faces of this, the structure that I drew here, are called the prism planes. Okay, and these would have the index 1, 0, 1 bar, 0. Okay, so these right here, I'll draw it in a different color. For example, one of these is this front face. Okay, that front face is a prism plane. And if you look at that index, I'm using my rules now. Okay, so H is 1, K is 0, so I has to be negative H plus K, it's negative 1. Okay, and that's useful because I could look at other planes, like for example, I might look and say that something with a different combination of these that looks similar, 2 1s and a 0, are related. Okay. We also want to describe what's called the pyramidal plane. And these have the index 1, 0, 1 bar, 1. So they're just like the prism planes, but they have some component in the z. So that means they're inclined a little bit. Okay? So I can draw that here as this plane that I'm outlining in blue. Okay? So it's like if I took that front face and I tilted it back just a little bit. So it is possible to take and draw this crystal structure in a cubic cell. And well, it's not really a cubic cell, but it looks like a cubic cell. So let me do that real quick. I'm going to erase this big hexagonal guy. And I'm going to draw, if we wanted to kind of make it look like what we saw before, what would we see? So I could draw some three-dimensional shape like this. Try to make this guy actually touch. Okay. So in a drawing like this, this is my c-axis. This would be A1, and this would be A2. Right? I could put atoms at each corner here. And then there would be another one inside this cell at a location that is 2/3, 1/3, and 1/2. Okay? But there's a few things we have to remember. So one is that not all the faces have the same length when I draw it like this. So this front and this side have the length A, but in the vertical direction, my cell has a length C. Okay? So it's not like the cube we drew before. The other thing that's problematic about this is usually when we draw something like this, we assume that all the axes have 90-degree angles to each other, and that's not true here. Okay? So A1 and A2 are actually 120 degrees away from each other. Okay? So it's still correct. It's just slightly less useful way of drawing the HCP crystal structure. Right? So the first thing you could do is you could think about packing in this way, and we kind of thought about it as if we wanted to do closed packing and we wanted to stack up rows of atoms, how would it work? So you could say, well, if I actually used hard spheres or used marbles or something like that, what would this look like? And an important thing you could go and predict with those marbles is the ideal C over A ratio, okay? So how tall would this hexagonal structure be compared to the distance inside that closed packed plane? So for the ideal ratio, it would be square root of 8 over 3, or 1.633, all right? But if we go and we plot what real HCP metals are, we're going to see something that's a little bit odd. So I'm going to make a little table with different metals going out this way. I'm going to put on beryllium, titanium, magnesium, cobalt, and zinc. And for each of these, I'm going to plot what the real C over A ratio is. Okay. And we can go and put on things, and what we can find is that some of them are lower than this ideal prediction. So beryllium and titanium are 1.567 and 1.587. So they're lower, okay? Others are bigger. So cobalt is 1.628 and zinc is 1.856. But then magnesium is relatively close. It's 1.623. Not exactly, but it's pretty damn close, right? So this tells us something. It tells us that although we had originally thought about these things as hard spheres, maybe that's how we think about how they fill space, it's not exactly right. And actually what this tells us is that there's some directionality to the bonding, okay? So in some cases that bonding is stronger and it wants to actually be shorter in that vertical direction than it would be just if things weren't interacting in any interesting way. And other times that those bonds are weaker and it wants to be taller and longer in that direction, okay? So when we want to start looking at this microstructure, we care about what happens with dislocations and plasticity, like everything else in this class. So we can go and ask the same question that we saw for FCC materials and say, okay, where would they be? Okay, and our answer is going to be the same thing. It's going to be that they're in the closest packed planes in the close packed directions, okay? These are going to be really the same thing we saw in FCC. We're just going to have that slightly different notation, okay? So that slip direction is going to be A over 3, 1, 1, 2 bar, 0, okay? It looks very scary, but if you put those vectors on that little hexagonal drawing we had before, what you'll find is we're just pointing from one atom to another, and we're just doing it in a slightly complicated way to match our Bravais-Miller indices, okay? And then the slip plane is going to be the 0, 0, 0, 1 plane, right? So these are those basal planes. And that would be the easiest place to have slip. So this is in fact called basal slip. All right? And it in fact is the most commonly observed slip. But it's not the only kind of slip that we see, okay? If you go and you look back at that hexagonal lattice, what we find is that this A over 3, 1, 1, 2 bar direction is also on the other two types of planes that I mentioned. It's also on the prismatic planes, and it's also on the pyramidal planes. Okay, so it is possible to have non-ideal slip. Which is pretty interesting and unique. And it really comes down to a simple fact. We're going to talk a little bit more about why. We're going to derive a reason why. But if you look at those basal planes, they're stacked on top of each other. But when we're trying to plastically deform something, we're trying to give it an arbitrary shape change. And we need to have slip along all different planes to give us that arbitrary shape change. And it turns out that it's very hard to have that with just basal slip. You need to have some other mechanisms active. Okay? We'll derive it later, but it gives you a sense of what's happening. So it turns out that this is more likely for materials with non-ideal packing too. So for example, titanium and zirconium can often exhibit slip on the 1, 0, 1 bar, 0 planes. Okay? These are those prismatic planes. So it's very common if you go into an experiment to see that. So because but if we sort of think about basal slip, we're having slip on these closed packed planes in the closed packed directions. It's very, very similar to what we saw in FCC. Okay? We have it's the closest packed direction. Okay? But if you remember, what was almost the first thing we did with FCC materials? We said that, well, that's great that these are the perfect dislocation vectors, but we said, is there another path? Can we have partial dislocations? And sure enough, we can also have partials in the HCP crystal structure. Okay? So if we think about our full or perfect dislocation, its Berger's vector is A over 3, 1, 1, 2 bar, 0. We want to do the calculation and think if we could have partial dislocations as well. And here we would have it splitting into two partial Berger's vectors. One would be A over 3, 1, 0, 1 bar, 0. And the other would be A over 3, 0, 1, 1 bar, 0. So, by the way, just a reminder, you can go back and check. We're still hitting our limits set by our Bravai-Miller rules. Okay? And if for both of these, we go and we calculate what's the magnitude of the Berger's vector squared, we're going to get it's A squared here, and it's 2/3 A squared there. Okay? So we have the same thing. This is less energy than the full, and it means that the partial dislocations are preferred. Okay? The one thing you'll notice is that this number, this Berger's vector squared, is not exactly the same as what we calculated for FCC. It's not a trick. It's not a math mistake. It's just the difference in what A means, right? When we were talking about A in FCC crystal structure, we were saying that was one of the faces of that cube we drew. It wasn't the distance, the closest distance between two atoms, okay? In the HCP crystal structure, A is the closest distance between two atoms. So they're not the same A, right? Nothing's wrong, it's just they're not the same A, right? So we end up having something that's very similar. We have a reduction in the dislocation energy, the strain energy in particular. And then if we do the math, we'd find that those partials lie at 30 degrees from the original dislocation Berger's vector, okay? So it's the same thing we saw in FCC. We now have mixed dislocations. Okay, so if we started with an edge, we now have something with an edge plus screw character. If we started with a screw, we now have something with an edge plus screw character. And we can have all the same complications that we saw in FCC. We can have these partials gliding along planes. We can have them interacting. Sometimes they have to recombine before they can do things inside of our crystal structure. Okay, so I'm going to stop this video. I need to go do something else for a minute, but then I'll come back and I'll do another one on body-centered cubic materials. So our third type of crystal structure that we're really going to spend a lot of time on. All right, thanks.